Good afternoon, everyone. We'll wait for 2 more minutes and get started. Yeah, let's get started. So, getting so, we have one announcement that in the group the that was created recently. You will all of you will be added in that group, and ML projects will be assigned to you. You can ask any questions regarding the projects. If you have any doubts or anything that you want to ask related to the project, you can post it in the group. Each group will have three people, and one ML project will be given to you to be completed. So previously we were seeing supervised and unsupervised learning tasks. So supervised task would be classification of, say, we have images, say, of dogs, cats, and some horses like that. We have data and the labels along with that data. This kind of classification task would be a supervised learning task. If we do not have labels for the data, it would be an unsupervised learning task. So within these tasks, there are two kind of differentiations correspondingly. Say there are classification and regression. So classification would be having to predict discrete values. Regression would be having to predict continuous values. Example might be predicting a grade would be a classification, classifying a bunch of people into different categories. Uh, Predicting the percentage that a person might get would be a continuous variable that would like to predict. So it would be a regression problem. So in unsupervised learning, we have di- uh, clustering and uh, uh, dimensionality reduction. So what we do is in clustering, we try to plot all the values on a graph and try to see which kind of uh, roughly in which kind of area all the dots lie and try to classify depending upon it. Here we have an Irish data set that contains sepal width, sepal length, petal width, and petal length. Uh, we also know the classes here. Suppose we do not know the classes, by just plotting the values on the graph, you can say there might be two kind of clusters here. All the dots here are roughly together, and all of these dots are roughly together. If you do not have labels, we can just roughly say there are two clusters. But since we have labels here, we can actually see that there are three different classes. So there are different kind of clustering algorithms also available for us. Next comes the principal component analysis. This is just finding out the eigenvalues and eigenvectors, removing all the eigenvectors corresponding to the low eigenvalues. We just pick the highest, say suppose we might pick top 10 uh, eigenvectors. If it has say some thousand uh, variables, so we have, let's say, suppose we have 1,000 features for each data point, and we want to keep the columns or keep the features that have most information related to the task that we in our hand. So what we do is we try to find the eigenvalues and eigenvectors of the 1,000 dimensional space. And then we might choose top two, top five, or any number of features that we would like to keep. Say suppose if we extract two uh, principal components from the four data points or the features that we had, sepal length and width, petal length and width, right? From those four, we are trying to extract two directions, two eigenvectors that have the most information along with them. So doing that and plotting those values, we found out this is one of the plot that we get. We can do one more thing is the scikit-learn library. There are a lot of things available for us in scikit-learn. So here you can see there are different algorithms that are available in our scikit-learn document library. So there are some cluster functions. So all these are different algorithms in clustering. So here we have the functions that are available and also the classes that are available. So it's the same thing. If you want to create a class and try to do some inheritance that you might use in the further thing, you can use the class thing here. Or else if you just want to do you utilize it just for once, and you can use the function. So you can go through all of these things. So there are different data sets also available that are pre-built into the scikit-learn. So you can go through like different data sets, and you can uh, do some experiments and get your hands dirty. So I would suggest you start with this California housing data set. It will try to predict the housing prices re- given different features of the house. Where is it located? How much length is there? How much width is there? What is the area? Is it a beach facing property? Different kind of properties that are available for us. You would like to predict the cost of the property. So cost might be a continuous value. So this comes under a regression problem. So there are a lot of data sets available for free from the scikit-learn document library itself. You don't have to understand each and every model that is here. You just have to know what are different models available, or the superficial, like there are classification models, there are clustering models, there are feature selection models. Uh, Different type of models available, and once you implement things, you will do experiments with each model and try to find the best model that gives you the best performance. So now the question comes is, how do we evaluate or how do we say that this model is better and this model is not good? So how do we test ourselves? We have an exam. So in our exam, we have some marks are given to us depending upon our performance. So a set of syllabus will be given to us. We'll try to learn some information from that syllabus and try to implement that information that we grasped and implement into a test. So in a model, we have, say, let's suppose we have 10,000 images. What we do is generally divide it into 80-20%. 80% will be the training data, 20% will be the testing data. So the model will try to learn from the 80% and will test how good it is performing on the 20% data that the model hasn't seen before. So it's similar to like having some a similar kind of question, but that you haven't seen before. You have to understand the topic that's being explained. You'll grasp it, have some understanding. Using that understanding, you'll try to answer the questions in your test. This is similar to that. So a model will train on the training data, that is 80% of the total data. Using the information that it has learned, it will try to predict the answer for the set aside 20% of the data. So these 20% of the data, we have the labels corresponding to them. So say suppose if the image is of a dog and we label it as 1, and image is of a cat, we label it as 0. So if the model sees a dog, it should predict 1. If the model sees a cat, it should predict 0. So say suppose in our test case, we are saying that given a dog image that is 1, it is predicting 1. So we'll subtract these two. 1 minus 1 would be 0. This is correct. If it predicts 0 and the image is of a cat, and 0 minus 0 would be also 0. So we do not penalize anything onto the model because it is giving us a correct answer. But if a model is saying 1 for a cat, it will be 1 minus 0. So will penalize the model by 1. Similarly, if it is predicting dog, but it is a cat image, the will penalize it by 1 because the difference between them is 1. So it is a modular difference. So this thing that we just saw is called a loss function. So in our exams, we have a set of marks that we try to achieve. We try to achieve 100%, right? So if we do not have 100%, say suppose we lost like 20 marks, so we'll get 80 by 100 marks. So more we pin the teacher would penalize us by 20%. So suppose we got 0% out of the 100%, the penalization should be heavy, right? So for each and every dog, it is saying cat, and each and every cat, it is saying dog. So we penalize, say for first image, it predicted correctly. We do not penalize. For the second image, it predicted wrong. So we penalize by one. In the next image, we do not penalize. So we will go through all the images that in our training set. We accumulate all the losses that were for each image prediction. We'll have a loss. We'll accumulate all of this, and this is called the cost. Like how much should the model be penalized finally? So by dividing the cost by total number of images that went in, it would be a nominal fraction by which we can judge how wrong the model is. If the model is predicting all the values correct, it would be all zeros, and we'll accumulate zero at the end. So we do not penalize this cost. How much ever the cost we get, we penalize the model. So for single data point, we have a loss. For the whole data set, we will be having cost function. We'll calculate all the cost that has been created for the training data set. We'll penalize the model by it. And then we'll try to train it again. Now on the second time, it has seen the information before. It will try to adapt itself such that the penalty will be low for us. So it's similar to our exams, right? We'll try to do some quizzes, daily assignments, so that we'll do have some practice. We're training for it. And then when the final test comes, we'll have to predict the answer, or use the information that we have and try to predict the answer for the question. So slowly by training our model and by penalizing, we'll slowly achieve a better accuracy on the prediction. So to make this uh, train test split, we have a uh, uh, API called train test split available for us. So let's see. So here we have a data set called MNIST. MNIST is a handwritten digits data set that was created in 1997. So here we have 1,800 images of 8 cross 8 shape. Let's plot one data point and see. So see. So each here we have each grid is a image. So there are 8 cross 8 pixels available for each image. So in total there are 64 pixels. Each pixel can contain value from 0 to 1. 0 would be the lightest and 1 would be the darkest. So here you can see by different set of dark and light patches will kind of resemble the numbers that we have written. So here you can see all these are zeros, and there are labels given 0, 0, and 0, 0 like that. For all ones we have labels here. So for different images we have different labels. So we do x dot shape. This is saying that, see, we have 1787 images. Each image is a 8 cross 8 image. So there are 64 data points for each entry. And y value would be the number that we have, 0, 1, 2, 3. So if it is this is a classification problem, right? Given some image, we are trying to predict which class does it belong to. Those classes are between 0 and 9. So if similarly, if these images are cats or dogs, we'll try to map the name to a number. So like a cat equal to 0, dog equal to 1, horse equal to 2, like that. Since here we are directly using just the data set is of numbers, we'll directly use the label of the data to the number itself. So why are we doing this? Why can't we just put cat, dog, uh, cow, zebra, horse, try to predict the word? So machine will only understand zeros and numbers, right? Only things we using binary. So we'll convert the labels into some numerical format, saying that cat is 0, dog is 1, things like that. Here is also the same thing, but here we have in the image we have numbers, and we map the same number that's in the image to the label that we have. So here we have, see, these many images are there, and each image is 64 pixels. Uh, there are, for each image in this section we have a label, which class does it belong to. Now we had previously had these many data points, and here we had 64 uh, uh, features, 8 cross 8, 64 pixels. Now we are trying to, this is a 8 cross 8 square matrix, right? So we are trying to extract the eigenvalues and eigenvectors for this matrix of 64 digits, sorry, 64 pixels. And we'll take the top two number of like best two principal components, or the highest eigenvalues, highest eigenvectors with eigenvalues. Sorry, highest. We'll select the eigenvectors that have the highest eigenvalue. So here we have 64 features, right? So by after compressing everything, we'll just keep two principal components that will have the maximum projection of the 64 data points onto a 2D plan. Here previously we had, here see, just converting this 1864 into some 1800 comma 2. So it went from 64 pixels to 2 pixels. Now using this data, if we try to classify, if we try to cluster, let's see what happens if we plot them, these two vectors. So previously in the iris data set, we did the principal component analysis and try to plot it here. So the same thing we are trying to do. Previous it was 4 features. Now we have 64 features. Now 64, we are compressing everything into 2 features called principal component 1 and principal component 2. So each value would be sorry, this is just some syntax that is available. We're just trying to plot all the points here. So here we have on this axis is the principal component 1 and this axis will be principal component 2. Then we are plotting all the numbers. Since we have the labels available, we can see there are distinct values that are here. All the zeros are here roughly. All the nines are roughly here. So 9, 8 and 7 and 9 are a bit similar. Let's say this is 8 and these blue digits, blue dots are 3. So most of the time in these small kind of pictures, we might easily get confused between 3 and 8. And that's why we can see that these values are a bit closer. So there is rarely a number that looks similar to 4. So all the fours are a bit close together, but they are a bit isolated from rest of the group. Similarly, zeros. So these zeros might have some distinct values when compared to the rest of the things. A zero might be roughly closer to 6, right? Some depending upon the pixel density, and we might slowly get confused between 0 and 6. So those points are in between this junction. So just by compressing that 64 data points into 2 points, we can plot it and directly see and extract some information from it. This information might not be the exact reason or exact thing, but we can do some preliminary ideas. Like when we can develop some preliminary ideas to create an hypothesis, saying that the similar thing that I just said, right? So 6 and 9, 6 and 0 are a bit close together. It might be that more sixes might be looking like nines, right? Or zeros. Sixes are looking a bit like zeros. So they are a bit close together, and zero is very far away from looking like a 4. Now we are extracting x train x. One second. So we need to import. So from sklearn dot model selection, we need to import test train split. What does this test train split does is it will take in the x and y values, the data and the labels. It will split to two sets. That the first set will contain uh, training data and the second set will contain the testing data. So x train, x test, y train, and y test. This is how we will unpack the data, and then we are creating a class called model that inherits everything from the Gaussian naive Bayes model. This one was written in scikit-learn library. We are trying to utilize that algorithm. We are creating a model and trying to fit that model onto the X train and Y train data. It will see the X train data and try to predict the Y train data while people are being distracted here. So people might be a bit distracted here just by seeing there are X train, X test, and sometimes you may also might see X validations. So what does validation mean is like, so we have 100% data, we'll take 80% test and sorry 80% train and 20% for the test. So within this 80% data, again we'll do a split, saying this amount of data will be used for training and this part will be for validation. So we can rotate from this 80% only, we can pick some 10% as our validation data and train on the rest of the 70% on data. And this continuously training and validation would be a best or the best way to do a perform like a machine learning model. So you'll sometimes see train, test, and validation. So validation would be for the after training a model, you will validate it on some validation data. So if we have the whole thing, all the data set is available for us, we'll have train, test, and we'll try to predict on the test cases because we have answers for the predicted cases. But say suppose we are trying to predict the weather for the next month. We do not have the label data for that, right? So we have to wait some time to get the value to find out the loss. So what we do is we would like to forget about the testing part. We'll have the data say from 1950 to 2020. So we'll take the data from 1950 to 2010. We'll try to give this data to a model. It will learn information from that, and we'll try to use this model to predict on 2010 to 2020 that we put aside. So then after going through different models that are available in our scikit-learn library, you can uh, come to a rough estimate of which model is performing the best. Now you can test this best performing model on the test data. So since in our example we do not have any test data, it will be the final prediction, and we'll wait for one day to see what is the weather like, and is our model predicting the exact value. So sometimes it might happen that you'll see test, train, and validation. Sometimes it would be test and train. So we are sending that data into Gaussian Naive model. We initiated that model into this class into a variable called model. This Gaussian Naive contains a method called dot fit. All the all these functions or classes will have an inbuilt method called fit that does the training for us. So we have y model dot fit y train and yx. It will take the data from x train and it will try to predict the y train. And for the real time thing, we do model dot predict x test. It will predict the value. It will predict the value of y and it will assign something to it called y model. So the difference between the predicted and the label thing would be the main thing that you need to understand. So here we can see just by getting that numbers, we can directly do some just a linear plot to get the prediction for this. And after our model is trained, we try to predict the accuracy on the test data. So here we see that you are 83% accurate in your prediction. So as long as this value goes up, we are trying to achieve the best accuracy ever. So this is a similar kind of plot that will confuse a bit of the humans, but this is a small rainbow six is the sources where the misleading points will tend. For example, the large number of 2 points are saying that these values are being predicted. See, all the threes are being predicted as three, and the different things are. So the seven is being 1 3 is being predicted as seven. Five of threes are being predicted as eight. So here you can put instead of different color, you can put rainbow color, and it will just show different kind of colors. Previously we saw here, right? So different colors just to visualize things. Now let's move on to the next part. So here you can see that the train and test validation split that just was talking about. So after we have trained two different models, we have two different accuracies for each model. So you can use this, say suppose this is our train data, and this whole white bar we are extracting for the train part, and this part we are setting for validation. This is on our first trial. In the second trial, we'll put all the white space as our training data, and this part as our validation data. And there will be some test data also available if we haven't done the 80-20 split. This is the whole 100%. If we have done the 80-20 split, we'll have some 20% of data available for us to do our test. This test data is never seen by our model. In these different folds, we are trying to train each model with a different set of data to see what is the best model. But in each trial, some part of the training data is not seen by the model, and we are trying out the validating our model on this validation set. But the test part will never be seen by our model. This is like predicting the final outcome. So it is just called making these kind of different folds is just called cross validation, just to have a good authority on how accurate is our model. So now comes the bias and variance trade-off. So here you can see if we are so roughly this plot, we if we try to predict using a linear model, we will try to fit a single straight line. So there is some kind of deviation from our data. If we put lot of like a large number of non-fit like so this is just y equal to mx plus c, right? So here we have some y equal to m power 20 x. Sorry, y equal to m power so mx power 20. So this is a 20-degree polynomial. Here we are trying to fit a single degree polynomial onto a curve. Here we are fitting a very high, large number, having a very high ups and downs that will try to fit each and every point. So this might fit exactly to our data, but it is not useful for us. If there is no data point, we can roughly say in between these 2 points, there might be certain point somewhere here, but our model is trying to predict exactly on our training data, and it will not easily generalize. So this kind of thing. So here you can see we are using y equal to x plus b. You can use a third degree polynomial also to fit it. Here we are just creating those random numbers, some random data, just to do show us some experiments. So here you see. So first degree polynomial is a single straight line. So second degree polynomial or the third degree polynomial is a cube, right? So it is a bit more orange thing. It is a bit more like closer to the exact values. The fifth degree polynomial is fitting better to the values. If we keep on increasing, it will exactly fit all the points that are available. So, but it will not easily generalize. If we do not put give a bit more freedom, it will just try to just fit a single straight line. This will give us a bit more inaccurate prediction. It will generalize well for the model, but the accuracy will be less on the testing data. If we give similarly, if we give a high degree of polynomial also, it will fit accurately to our training data, but it will not generalize to our test data. So these two are like two sides of a coin that you need to balance somehow. So you need to find best fitting polynomial that's not like very extremely biased towards the training data, but also not very loose, just predicting a single straight line. This is called a hyperparameter that we would like to uh, tune. So few of these library names, so these model names have been changed. By just clicking the Stack Overflow button, you can go through the Stack Overflow page and just copy paste the this import. What is the name of the module that contains validation curve? This will be just a small practice for you guys. So here you can see this kind of plot is the best kind of fit for us, our data. So these learning curves, once we have gone through one or two models, we'll go through this what is training score, testing score or validation score, training loss, validation loss, how to plot, how to understand different plots. So this is like training score should always go down and validation score should always go up. This is a general thumb of rule. By in the next class, we'll go through a practical example and see how this differs. So this is a bit more advanced. How to find if there is here we just have only one thing that we need to change, right? Or what is the degree of the polynomial? So it's like a single knob that you need to turn to find the best result. Say suppose if you have two or three more knobs, how do you find the best thing? You will turn the first knob by 1 point or do all the experiments. keeping the first point the same, we'll change the second point and do all the experiments. So there will be a grid that will form containing different parameters, like different values for different hyperparameters. So we'll try to find best values for different parameters. This is called grid search. On a practical example, we'll see all these examples. So if you have any questions, you can ask me. You can message, type in the chat, or else you can either type in the chat or else you can unmute and ask. So just a reminder once more that in the WhatsApp groups, we'll be posting the my ML projects that each group, we made the different groups and each group consists of 3 people. We have assigned a ML project that you need to complete for the during the internship duration. So any doubts, once you see the name of the project, just try to go to kaggle.com. So in Kaggle, you can just search for your data. So suppose one project I remember top of my head is weather prediction. So in Kaggle, we just come. So there is some challenge called weather forecast. So in this has some data related to that. You can come here, just create an account here and come here and you can download this data set. So since this is a competition, this is a free competition, anyone can enter. You just have to sign in and register here. So here you will find the data, and using this data, also there are codes and discussions available. You can directly search your task here. So weather data. So you'll have some data sets available, some more notebooks also. So there will be some code also related to each data set. You can go through them, get a general idea. So here we see some COVID-19 forecasting. Some data is given and we are trying to predict something. So people have done different type of analysis. So here we can see there are here temp, max temp, min temp. There are different features available, and here they have written some code that will extract and create a pandas data frame. So this will be your data set. You can go through it. What are the things available? Are there any null values? All the code will be available here. You just need to run it, get the data, and inside this Google Colab, you can use the Google Colab environment, and all the things that are available have been installed previously for you. So you do not have to try to install different libraries. All the required libraries have been installed. Once you have gone through one small project, then you will understand what are different libraries. Then you can go out of yourself and try to get libraries and install. It's not that difficult, but just it will be a bit overwhelming for you to install different libraries, right? So that's why in Google Colab is providing everything that helps you to get started. Go through this regarding your project. You can come here, try to find previously done data sets and competitions or the different notebooks. Go through them, try to understand what's going on, and then you can go and find your own data set and you can do your own analysis. This is just for like examples that you can go through, like inside your chapter there will be some examples that have been solved. At the end of the chapter there will be some questions that you need to solve, right? So this is kind of those examples. This is a very good website. You can find most of the things here. Thank you guys for attending. If you have any doubts, post it in the group. I'll be in that group answering your questions. I think once you have your project and once you will get download your data, you'll have much more hands-on things that you need to do, and you will be more active in our classes also. I hope you are going through the Andrew NG lectures. Uh, If you do not have any doubts, you can